You saw in the last lecture how just considering the electrons in a conductor to be free particles in a box, you could get a reasonable impression of the quantum mechanical behavior of those electrons, what the allowed energies looked like, what the behavior of the metal was even, to some degree. We were able to calculate, for instance, the degeneracy pressure of the electrons in that state, and get an answer that was comparable to the measurable physical properties like the bulk modulus of the material. That free particle assumption seems very fishy, though, because those conduction electrons are going to interact with the atoms in some way. So what I'd like to talk about in this lecture is how we can include the atoms and the results, in particular the band structure of energy levels in solids. Including the atoms in the behavior of the free electrons in a material, for instance, is a rather complicated process. You might think about an electron coming in towards some atom, where we have electrons orbiting the nucleus of the atom, and how these particles might interact. Now, we know from quantum mechanics that this picture is just plain not correct, that we need to consider the electron as it approaches the atom as some sort of a wave packet. So I'll draw some wave fronts. And the atom itself as being composed of a nucleus, which has almost negligible wave nature compared to the wave nature of the electron, since the nucleus is so much heavier, surrounded by some cloud of electron. Describing the interaction of a wave packet like this and an atom with an electron cloud surrounding it is a very complicated process in principle. But whatever the interaction is, it's going to be encoded by some Hamiltonian, h hat, which is going to include the kinetic energies of the particles and then some potential that tells you how the energy of this interaction takes place. If the electron were very close to the atom, would there be an attractive force? Would there be a repulsive force? Would there be an increase in energy or a decrease of energy? Now, typically you can assume that the potentials like this are related just to the relative displacement between the atom and the electron, so some difference between the position of the electron and the position of the atom. Perhaps the potential even only depends on the absolute magnitude of that vector, only depending on the distance between the electron and the atom. Either way, these potentials can come in a variety of forms. But if you're trying to consider a material with many electrons and many atoms, what you're going to have to work with is actually going to be a sum over all the atoms of the material of the contribution of each atom to the energy of an electron. If we have multiple electrons, we'll have to have lots of different kinetic energy terms, and we'll have to have a sum over electrons here as well. So this is a very complicated Hamiltonian. We can't really hope to solve it analytically. We can, however, make some analytical progress if we make some simplifications. And I'm going to make 3 simplifications for this lecture. First of all, this potential, which is in principle a function of the distance between the electron, the position of the electron and the position of the atom, I'm going to pretend it only depends on the magnitude of the distance, and I'm going to make a very crude approximation to this potential, namely that if the electron is right on top of the atom, it experiences a very strong repulsive force. If the electron is displaced from the atom significantly, the atom overall looks neutral, and there is no energy associated with that reaction. The approximation I'm actually going to make then is that the potential contribution of a single atom to an electron is given by a Dirac delta function. Some proportionality constant describing the strength of the delta function times the delta function itself as the distance between the electron and the atom. So this is the potential that we're going to work with. This is just for an interaction between a single electron and a single atom, however, and we're going to have to consider multiple atoms. And in order to make any mathematical progress, we're going to have to know the positions of all the atoms. In any realistic material, the atoms will be more or less randomly distributed, though there may be some overall structure dictated by the structure of the bonds between those atoms. I'm going to assume a very, very simple structure here. I'm going to assume that we're working with a crystal. So we're working with a regular array of atoms, for example. Furthermore, I don't really want to mess with trying to express this regular array of atoms in 3 dimensions, so I'm going to assume that we're only working with a one-dimensional system. Essentially a one-dimensional crystal, just looking at a slice through a potential 3-dimensional crystal. This is not the most relevant physical scenario, since a Dirac delta function in 1 dimension extrapolated to 3 dimensions is sort of a sheet delta function, not an array of point delta functions like a crystal. So this is not the most realistic scenario, but it does actually reproduce a lot of the observed behavior of, well, real electrons in real crystals. The potential we're talking about here, then, is going to be a one-dimensional array of delta functions. So our v of x is going to look something like this. It's going to be 0 whenever you're not on top of an atom, and it's going to spike up whenever you are on top of an atom. And this is going to continue, potentially infinitely, in both directions. This is called a Dirac comb, since I guess it kind of looks like a comb, and it's made of Dirac delta functions. So this is the potential we're going to work with. The nice feature of this potential is that if these atoms are, say, spaced by some distance a, this is a periodic potential, and there are theorems that help us deal with periodic potentials. One of these theorems is called Bloch's theorem, and what it states is that for a potential that's periodic, namely the potential evaluated at some displacement a from the current position is just equal to the potential at the current position, the solutions to the time-independent Schrödinger equation for that potential can be written as follows. Psi of x plus a, displacing the argument of psi, is essentially the psi at the current location multiplied by some complex constant with magnitude 1, e to the I ka, for some unknown constant k. Essentially what this means is that the observables don't change. You know, multiplying the wave function by some complex number isn't going to, some complex phase, e to the I ka, isn't going to change the answer. Well, essentially what this means is that for a completely periodic potential, the observables aren't going to change from one period to the next, and that's more or less a requirement. Periodic potentials should have periodic solutions to the Schrödinger equation. We don't know anything necessarily about this constant k, but essentially what we're talking about, if we apply this to our delta function potential, or our Dirac comb potential, is atoms spaced apart by some distance a, and Bloch's theorem tells us that the wave function here gives us the wave function here, gives us the wave function here, gives us the wave function here. So we don't need to worry about the entire space. We can only worry about a sub-portion of the space. This is very useful. One unfortunate consequence of Bloch's theorem is that it only works for completely periodic potentials. So if we're talking about a material, a chunk of silicon, say, there are edges. In the inside here, we definitely have a periodic potential. We have a silicon crystal, we have an array of atoms, that's fine. We're working with something periodic. But at the edges, we're going to have problems. Since at the edges, well, the periodicity obviously breaks down. Under these circumstances, then, Bloch's theorem isn't going to apply. So we need to find out some approximation, some simplification, or at least some plausibility argument for how we can still apply Bloch's theorem to these cases. Well, we've already made a lot of simplifying assumptions, so what's one more? Our potential v of x is this Dirac comb structure that potentially continues to infinity. If we're working with a realistic material, we're going to have something like 10 to the 23 atoms here. As such, the contribution of the atoms you would expect, if you had a free electron here, it's going to be much, much, much more sensitive to the atoms nearby than to the boundaries of the material. As such, you wouldn't expect the edge effects to be terribly significant. So, one way to fix Bloch's theorem, if we're willing to ignore the edge effects and deal just with electrons near the interior of the material, is to take our delta function potential and wrap it around. Essentially treat this edge of the material as connected somehow through a wormhole to this edge of the material, wrapping the material around in a circle, for instance, working with a donut of material instead of a block of material. What this periodicity means, that we're assuming the potential is periodic overall, not just periodic from one atom to the next, is that our wave function psi of n times a, essentially the wave function on the right edge of our material, has to be equal to the wave function on our left edge of the material. And let me rewrite this. I have my wave function as a function of x, and if I add n times a, where I have n atoms from one side of the material to the other side of the material, times the separation of the atoms, I've essentially wrapped all the way around and gotten back where I started. That has to give me my original wave function back. So that's my periodicity. And under these circumstances, Bloch's theorem, which tells me how to displace my wave function by a certain amount, tells me what I need to know. Bloch's theorem gives us that psi of x plus na is going to be equal to e to the I capital N capital Ka times my original wave function, psi of x. My periodicity then means this is going to be equal to psi of x, which I can just cancel out then from this periodicity equation, giving me e to the I n capital Ka equals 1. That tells me that this capital K constant I have can only take on specific values. And those specific values are given by what will make the exponential 1, essentially 2 pi times an integer divided by capital Na. The argument here has to be 2 pi times an integer, and this is then the value of k that's going to give you 2 pi times an integer when you multiply it by n times a, essentially. So n now is going to be some integer, either 0, plus or minus 1, plus or minus 2, etc. Knowing something about this constant tells us how the wave function in one region relates to the wave function in the next region, and we have a variety of allowed values for this overall constant. So we have now what we need to solve the time-independent Schrödinger equation. The potential we're working with, and I'll just draw a chunk of it here, just with, say, 2 spikes. Let's say this is the spike at x equals 0, and this is the spike at x equals a. I'll add another spike here on the left at x equals minus a. We need to go through our usual machinery for solving the time-independent Schrödinger equation. We have our potential, and in regions, say, there, the potential v of x is equal to 0. Which means our time-independent Schrödinger equation is just going to be the free particle equation, minus h bar squared over 2m times the second derivative of psi with respect to x is equal to e times psi. You know what the solution to this is. We've done the free particle case many, many times. Our general solution is that psi of x is equal to a times sine kx plus b cosine kx, where k squared is equal to 2me over h bar squared. This should all look familiar. It's solving a second-order differential equation, essentially the simplest second-order differential equation you can think of. The subtlety with solving the Schrödinger equation under these circumstances is that the general solution in one sub-region isn't enough. We have to find the solution in all regions, which means we're going to have to match boundary conditions. So it's also useful to know then what the solution is at some other region so that I can match those two solutions together across the delta function. Bloch's theorem tells us that the solution in this region is going to be the solution in this region multiplied by some e to the ika, excuse me. Since we're not shifting to the right, we're shifting to the left, it's actually e to the minus ika, but our solution in this region, psi of x, is equal to e to the minus I capital Ka times our solution in this region, a sine kx, x plus a plus b cosine x plus a. So I'm writing now this x is referring to negative values, so I have to shift it over to make it correspond to the values in the other region, and I multiply by this overall constant to make sure everything matches up. So we have our solutions now in this region and in this region, and these are general solutions. We have this capital K in here, which we know a little bit about from the overall periodicity, but we also have this unknown K constant, which is given in terms of the energy. Now, typically, the solutions to the Schrödinger equation matching boundary conditions tells us something about the allowed energies, and that's going to be the case here as well. But these are our two general solutions. And let's figure out how boundary condition matching at this boundary works, since that's going to tell us something about the energy, something about these A's and B's, and so how that information all connects to these capital K's. So the boundary conditions we have are going to match these two solutions together. We have two boundary conditions, and just to recap, we have our delta function potential, x equals 0, and we have our solution in this region and our solution in this region, and we're matching them across the delta function at x equals 0. So the two boundary conditions we have for the wave function. First of all, the wave function has to be continuous. What that means is that psi of 0 plus has to be equal to psi of 0 minus. The solution just on this side has to be equal to the solution just on this side of our boundary. And if I plug these in, the solution for 0 plus, substituting 0 in for x, the sine term is going to drop out, since sine of 0 is 0, and the cosine term is going to go to 1, since the cosine of 0 is 1. So the b is all I'm going to get. That's all that's left here. This term's dropped out. This term is just equal to b. So my equation then is b is equal to whatever I get when I plug 0 in for the solution on this side. So substituting in 0 for x, the x's are going to drop out. And I'm just going to get cosine Ka and sine Ka, and my a and b, and my e to the minus I Ka. E to the minus I capital Ka times a sine lowercase ka plus b cosine lowercase k a. So that's our continuity boundary condition. The other boundary condition that we have to work with is that typically the first derivative of the wave function is continuous. The exception to that typical boundary condition is when the potential goes to infinity, you can have a discontinuity in the first derivative. And the only case that we know of that we can solve so far in this course is the delta function potential. We talked about this when we were doing bound states for the delta function. So if you're fuzzy on how this actually works, I suggest you go back and refer to the lecture on bound state solutions to the delta function potential. Otherwise, the equation we need to tell us how d psi dx is discontinuous relates the size of the discontinuity to the strength of the delta function potential. The equation, and this is equation 2.125 in your textbook, is that the delta of d psi dx is equal to 2m alpha over h bar squared psi. So we need to calculate the first derivative of the wave function from the left and from the right, subtract those two, and that's then going to be related to the value of the wave function and these constants, where alpha here is the same constant that we used to describe the strength of the delta function potential when we first introduced the structure of the potential. So if you actually go through, calculate the derivative of this with respect to x, the derivative of this with respect to x, what you end up with is, well, the derivative for this, we're then evaluating our derivatives at x equals 0, and a lot of the terms drop out. The derivative of this term from the plus direction at x equals 0 is k times a. This is a lowercase k now. The derivative from the left, derivative of this potential with respect to x, evaluated at x equals 0, is e to the minus I capital Ka times a lowercase k from the derivative, and then capital A cosine Ka minus capital B sine Ka. That's the left-hand side of our discontinuity equation here. Discontinuity in the first derivative then being equal to 2m alpha over h bar squared, and the value of psi at 0, well, I could use either the left-hand side of this equation or the right-hand side of this equation, but, well, left-hand side here is much simpler, so I'm just going to use capital B for the value of my equation. Now we have two equations and we have a lot of unknowns to work with. We have capital A, capital B, capital K, and lowercase k. But it turns out we can come up with a useful relationship just by manipulating these equations to eliminate capital A and capital B. Essentially, what you want to do is you want to solve this equation for a sine Ka. Multiply this equation through by sine Ka so that we have an a sine Ka here and an a sine Ka here. and then use the result of solving this equation to eliminate capital A. So making that substitution, we're going to have a capital B from this equation. So you'll have a capital B in this term, capital B in this term, and then capital B in this term, as before, which means you can divide out your capital B's. So you've successfully eliminated both capital A and capital B from your equation. The subtle term, as far as simplification goes, is trying to get rid of this e to the minus I capital Ka. But if you make the appropriate simplifications, you can reduce this down not to completely eliminate capital K, but to at least get rid of the complex form of the exponential. You end up with a cosine e to the I capital Ka when you finish solving this. So, subject to a lot of algebra that I'm skipping, the end result here that we can actually work with can be expressed as cosine capital Ka is equal to cosine lowercase ka plus m alpha over h bar squared lowercase k sine lowercase ka. So this is an equation that relates lowercase k, which is related to our energy, to uppercase K, which is what we got out of Bloch's theorem, and the strength of the delta function, the mass of the particle. This is then going to tell us essentially the allowed energies. There were very few restrictions on the value of this capital K. That was just related to some integer. The equation then, just copying it over from the last page, can be expressed, well, this is just the previous equation. Capital K is related to some integer n, and lowercase k is related to the energy. So if I look at the left-hand side here, what do I actually have to work with? Well, my capital K, think about the set of allowed values for capital K. Cap K, just being related to an integer, which can be positive or negative, is going to have a lot of allowed values. Keep in mind now that capital N here is something of order 10 to the 23, so we have a very large number in the denominator, and we have potentially relatively smaller numbers in the numerator, so capital K is going to have very densely spaced allowed values, going, over the allowable values of n, which are essentially the integers, up to some very large number. So my allowed space of capital K values are densely packed, negative and positive. Keep in mind, however, that my capital K's are being substituted into a cosine. So no matter what I use for capital K, it gets multiplied by A. I'm going to have something between 0, or between minus 1 and 1 for the outcome here. The right-hand side of this equation depends on lowercase k, which depends on the energy. So you can think of lowercase k here as being essentially the energy of the state. So we have something that depends on the energy, and it looks like cosine of something related to the energy plus some constant times sine of something related to the energy divided by something related to the energy. You can simplify these a little bit. In particular, I'm going to redefine a variable z equal to lowercase k times a, which means this is going to be cosine z plus some constant times sine z over z. So I'm going to define beta being equal to, where'd it go? It's going to be m alpha a over h bar squared, leaving me with a ka in the denominator. So my right-hand side now, which is what I'm plotting here, is going to be cosine z plus beta sine z over z. So if I plot my right-hand side for a particular value, in this case I'm using beta equals 10, beta just being a combination of the strength of the delta function, spacing of the potentials, mass of the particle, and Planck's constant, you end up with a function that looks sort of like this. It looks kind of like sine x over x. Well, it does. But this z parameter is now related to the energy. So essentially we have an x-axis here that tells us the energies, and we know we can have solutions whenever it's possible to solve this. Our capital K space, densely packed with allowable values of capital K being plugged into cosine, is going to give us very densely packed values of, well, essentially the y-axis here, whatever the y-coordinate is. Since there are so many allowable values of capital K, since capital N here is a very large number, you can think of these essentially as a continuum of allowable values on the y-axis. The places where I have a solution then are going to depend on, well, the right-hand side of my equation, which is only between -1 and 1 for certain values of the energy. So these shaded regions here, where the energy of the state is such that the right-hand side of this equation corresponds to values between -1 and 1, for which we can find a nearby allowable value of cosine capital Ka, these are the allowed energies. And they come in bands. There is no single isolated value of the ground state energy. There is sort of a continuum of allowable energies, subject to these approximations that capital N is very large, for instance. So if we're dealing with a macroscopic chunk of material, the allowed energy states for a free electron that's encountering these atoms are going to come in energy bands. This is actually a really, really nice result because it allows us to understand a lot of the properties of things like conductors, insulators, and semiconductors. If, for instance, we allowed bound states to exist as well, they would have negative energies. So our free electron states are going to appear in separate bands. Our bound states are also going to appear in bands as well, and you can verify that by going through the solution process using delta function wells instead of delta function barriers. But if we have no bound or no free electrons, if we just have bound electrons, if we just have states down here, essentially, we don't have enough free electrons, don't have enough electrons, period, in this state to occupy all of our possible bound states, then we have an insulator. If we have states populated, again, same as in the previous lecture, starting with the lowest energy and populating states as you go up, you'll have an insulator until all of these bound states are filled. Once you start filling states in this first sort of energy band of free electrons, you have a conductor. It's very easy for electrons in an energy state here to shift to another energy state of slightly higher or slightly lower energy that may be slightly displaced in the conductor. So it's possible for an electron to move from one side of the conductor by moving from one of these free particle states to another. If we have all of our bound states filled and a complete conduction band, or a complete band here, also filled, well, that's going to be an insulator again, because it's impossible for electrons to move from one state to the other if all of the available states are filled. The only way for an electron to effectively become free here is for it to jump up to the next energy band across this gap. So we have gaps between our bands. And that determines whether or not we've got a conductor or an insulator. A third case that you've probably heard of is if we have, well, all of our bound states filled and almost all, or perhaps just a few, states in the next energy state filled. This we would call a semiconductor. It can act like a conductor if you have these few extra electrons filling the lowest energy states in a mostly empty band. But if you lack these few electrons, then you've gone to the insulating state. So they're states that are sort of on the boundary between entirely filled and mostly empty. And if you add a few electrons, it acts like a conductor. If you subtract a few electrons, it acts like an insulator. And this transition between conductor and insulator is something that we can arrange chemically and electrically, and this is essentially the basis of all of semiconductor physics. We'll talk in the next lecture about how semiconductor devices like diodes and transistors actually work in the context of these allowed energy bands and what sort of chemical modifications happen as a result. Another note here is that the temperature affects the energies that are allowed here. The next section in your textbook after this talks about quantum statistical mechanics, which tells you about, as a function of the temperature of the material, how these energy states are likely to be populated. The approximation that we're making here by saying start filling the energy states from the lowest energy possible and continue until you run out of free electrons isn't entirely accurate. That's essentially assuming that everything is at absolute zero, that there is no additional energy available to these materials. Now, conductors, insulators, and semiconductors behave differently in the context of temperature. Because, for instance, consider a conductor, or consider an insulator. If I have an insulator like this, or an insulator like this, if I add energy to that insulator, I'm essentially going to be contributing some additional energy to some of these electrons, which would otherwise be filling the lowest possible energy state. So I would be kicking them up to higher energy states. And if I have an insulator like this that hasn't even filled all of its bound states, well, adding energy is going to kick them up to higher energy bound states. It's unlikely to make those electrons free. But if I have a conductor that has entirely filled a sort of free electron state, and I add energy, I may kick more and more and more electrons up to the next higher energy band, transitioning that insulator into a conductor. So if I have an insulation material and I increase the temperature, the conductivity of the material tends to increase. If I have a conductor, on the other hand, and I add energy to these states, well, I'm not actually making any more free conduction electrons. I'm more just rearranging existing conduction electrons. And that rearrangement actually happens to be unfavorable under most circumstances. The classical explanation that's usually given is that as you increase the temperature of a material, the orderedness of the material goes away. Essentially, that nice periodic array of delta function potentials becomes slightly disordered, and that disrupts the band structure and makes it more difficult for electrons to transition from one energy state to the next. Thinking about it classically, the electrons are more likely to collide into atoms that are vibrating rapidly than into atoms that are nice and stationary. So if I increase the temperature of an insulator, I make it more conducting. If I increase the temperature of a conductor, I make it less conducting. If I increase the temperature of semiconductors, you can actually do some math to figure out what's going on. I'm not going to ask you to do that, but if you increase the temperature of a semiconductor, typically you increase the conductivity. So we can understand a lot of the properties of how insulators and conductors, even semiconductors, behave just with this simple periodic array of delta functions, which describes that the result are going to have the resulting energy states that are available for a bound or free electron in this material are going to come in bands. And the relative population of those bands determines essentially the nature of the material. To check your understanding of this, here are a few questions, namely asking you to recall what that trick was to figure out the boundary condition in terms of the discontinuity in the first derivative of the wave function at a delta function. Finally, describe how you suspect the solutions would change if the delta function wells had been used instead of barriers. We used barriers, assuming that if the electron was right on top of the atom, it would be strongly repelled by essentially running into the atom, but maybe it's actually attracted. Maybe there are bound states as well. Finally, going back and looking at that equation that gave you the energy bands, how do the energy bands look? What is their spacing? How wide are they, etc., as the energy becomes very large? And finally, there's this essay that's intentionally humorous, Electron Band Structure in Germanium, My Ass. I'd like you to read through that. It's fun. I'm not actually asking you to do all that much here. And then explain qualitatively what the plot that he describes should have looked like. For this lecture. First of all, this potential, which is in principle a function of the distance between the electron, the position of the electron and the position of the atom, I'm going to pretend it only depends on the magnitude of the distance. And I'm going to make a very crude approximation to this potential, namely that if the electron is right on top of the atom, it experiences a very strong repulsive force. If the electron is displaced from the atom significantly, the atom overall looks neutral and there is no energy associated with that reaction. The approximation I'm actually going to make then is that the potential contribution of a single atom to an electron is given by a Dirac delta function. Some proportionality constant describing the strength of the delta function times the delta function itself. Describing the interaction of a wave packet like this and an atom with an electron cloud surrounding it is a very complicated process in principle. But whatever the interaction is, it's going to be encoded by some Hamiltonian, h hat, which is going to include the kinetic energies of the particles and then some potential that tells you how the energy of this interaction takes place. If the electron were very close to the atom, would there be an attractive force? Would there be a repulsive force? Would there be an increase in energy or a decrease of energy? Now, typically you can assume that the potentials like this are related just to the relative displacement between the atom and the electron, so some difference between the position of the electron and the position of the atom. Perhaps the potential even only depends on the absolute magnitude of that vector, only depending on the distance between the electron and the atom. Either way, these potentials can come in a variety of forms. But if you're trying to consider a material with many electrons and many atoms, what you're going to have to work with is actually going to be a sum over all the atoms of the material of the contribution of each atom to the energy of an electron. If we have multiple electrons, we'll have to have lots of different kinetic energy terms, and we'll have to have a sum over electrons here as well. So this is a very complicated Hamiltonian. We can't really hope to solve it analytically. We can, however, make some analytical progress if we make some simplifications. And I'm going to make 3 simplifications. Including the atoms in the behavior of the free electrons in a material, for instance, is a rather complicated process. You might think about an electron coming in towards some atom, where we have electrons orbiting the nucleus of the atom, and how these particles might interact. Now, we know from quantum mechanics that this picture is just plain not correct, that we need to consider the electron as it approaches the atom as some sort of a wave packet. So I'll draw some wave fronts. And the atom itself as being composed of a nucleus, which has almost negligible wave nature compared to the wave nature of the electron, since the nucleus is so much heavier, surrounded by some cloud of electron. You saw in the last lecture how just considering the electrons in a conductor to be free particles in a box, you could get a reasonable impression of the quantum mechanical behavior of those electrons, what the allowed energies looked like, what the behavior of the metal was even to some degree. We were able to calculate, for instance, the degeneracy pressure of the electrons in that state, and get an answer that was comparable to the measurable physical properties like the bulk modulus of the material. That free particle assumption seems very fishy, though, because those conduction electrons are going to interact with the atoms in some way. So what I'd like to talk about in this lecture is how we can include the atoms and the results, in particular the band structure of energy levels, in solids.